When analyzing any significant dataset, we look for the center, the single point around which the entire population clusters. This statistical tool is known as a measure of central tendency. To find this center, we utilize three primary metrics: the mean, the median, and the mode. However, the mechanics of these metrics change depending on the state of the data being analyzed. In its raw state, known as ungrouped data, every individual value is listed. This transparency allows for exact, precise calculations. But as datasets scale, thousands of points are often compressed into binned intervals or frequency distributions. This is grouped data. This compression creates a resolution problem. Once the data is binned, the exact individual values of the original data points are no longer visible. How do we estimate the center of a dataset when we only have these opaque ranges? Moving from an intuitive guess to rigorous statistical programming requires us to translate the concept of middle into scalable mathematical syntax. Consider a small dataset of 5 values: 5, 8, 2, 4, and 6. Calculating the arithmetic mean here is straightforward. To represent this formally, we use the Greek letter sigma, instructing us to find the sum. We compress addition into this compact notation, starting at index 1 to n. Multiplying this summation by 1 over the total points gives the arithmetic mean. While the arithmetic mean adds values, the geometric mean calculates the nth root of multiplied products, which is used to analyze compounding rates. The harmonic mean uses the sum of reciprocals, a method that gives heavier weight to the smallest items in a dataset. Mastering this exact notation enables a data scientist to seamlessly program custom statistical operations in languages like R. Grouped data requires a different approach. Imagine a scenario where we only know how many people fall into height intervals, like 60 to 63 inches. Because the specific heights within that bin are hidden, direct summation is no longer an option. To solve this, we assume data points are evenly spread within each range, using the bin's midpoint as a representative value. We then multiply each bin's frequency by its midpoint, sum those results, and divide by the dataset's total frequency. This grouped mean is an approximation, trading the absolute precision of raw data for the ability to analyze massive datasets. Finding the median, the physical middle, in a grouped table requires a geometric operation more complex than the mean. We begin by identifying the median class, the specific bin where the 50th percentile of the cumulative data is located. To extract the exact median, we use an interpolation formula. The variable L represents our lower boundary. We calculate the exact steps to reach the center, divide by the median class frequency, and multiply by the class width. This process of linear interpolation allows a data scientist to accurately reconstruct numerical precision directly from compressed, generalized data. With the formulas for mean, median, and mode established, we must decide which one to deploy. The choice depends on the topography of the data distribution and the specific objective of analysis. The mode identifies the measurement with the highest probability. A marketing department uses the mode to pinpoint which specific ad format is driving most traffic. The mean serves as the strict mathematical average, where every data point influences the final outcome. Human resources uses the mean to calculate salary expenditures, where every dollar impacts the bottom line. In a symmetrical distribution, the mean, median, and mode align, but the mean is uniquely vulnerable to outliers. Because the median relies on physical position, it is immune to extreme edge values. While an outlier drags the mean right, the median stays firmly anchored. Real estate agents rely on median prices because a few multi-million-dollar mansions would skew the mean higher, distorting the view of a typical price. Navigating central tendency requires the data scientist to select the specific mathematical lens that reveals the objective truth of a dataset.